Okay, on part C of this question, it says find the length of an arc intercepted by a central angle of 1/4 radian. Okay, in a circle that has a radius of 3 inches. Okay, so we're going to try to find the length of an arc. Okay, and the central angle is 1/4 radian, and the radius is 3. Now, the quickest way to do that would be by using the formula that we used in our opener today, S equals R times theta. I'm not going to do that though, because that's going to be something we're going to develop here together in a second. We want you to think about the picture here, and knowing that the radian is defined as 1 radian as long as the arc length and the radius are equal. True? So in our particular case, if we were to draw our picture, okay, we know that the radius is 3, okay, and we have 1/4 radian here. Fair enough? So if that's 1/4 radian, okay, think about it, this would be an easy problem if that were 1, because the arc length would just simply be what? It'd be 3, wouldn't it? Okay. So as long as the radius or the radian measure of the angle is 1, then the radius and the arc length are equal. So we should expect that they're not equal here, because the radian measure is not 1 in this case. True? In fact, it's smaller than 1 by how much? It's a quarter divided by 4, isn't it? Okay. So the question is, what should that arc length be then? Keep in mind that if I have 1 radian and I go down to 1/4 radian, that's going to make the angle get smaller, which would in turn make the arc length get smaller also. Okay. And if it gets smaller by a factor of 4, then what should the 3 that it would have been change to? 3 divided by 4, and therefore the answer should be 3/4 then, shouldn't it? Okay. So if the radian measure, okay, got quartered, then ultimately the arc length would also get quartered. Fair enough? Okay. All right. All right, let's take a look at page 352. I want you to find next. Along with that, similar to that problem that we just did there, if you look at the example 2, part D of it, asks us to find the radian measure of the central angle that intercepts an arc of length S, okay, in a circle of radius R. So notice this time, instead of giving numbers like 3 and 1/4 like we had a minute ago, okay, this time we have just general measures of S and R. Okay, but ultimately what we can do is very similar to what we did with our previous picture that I drew. Okay, we can set up, and this is going to kind of lead us to that formula that I mentioned. Okay, if we have x radians, okay, that corresponds to S units, okay, for our arc length and our central angle. Okay, and we know that 1 radian, okay, is R units. Okay, and once we do that, then we can use the cross product property and do x times r and s times 1, and we get our formula here, which is s equals x times r. Now, I showed that to you in a different form at the beginning today, okay, that s, okay, being the arc length, x was theta, if you remember. This x represents how many radians the central angle is. Okay, the r represents the radius of the circle, and that s is the arc length. Okay. So it's just a different form of that same formula that I showed you earlier. Okay, and with this said, now we could theoretically go back and do that previous problem with this. We could just take the angle, which is 1/4, multiply it by 3, which is the radius, and we'd get 3/4 for the arc length. Okay, but like I said, I want to show you why the formula works. Okay, instead of just giving you the formula. And of course, we can manipulate the formula if we want to find the radian measure. Okay, we can do basically solve for x here, and we can do that arc length divided by the radius, and that'll give us the angle of the central angle measure. Okay. So with that said, we'll formalize that next. With our next slide here. So if the angle is a central angle in a circle, radius r, and if theta is measured in radians, then the length of the intercepted arc is s equals r theta. Alright, now here's the key again. I'm going to circle it, or not circle it, but underline it. The key is it needs to be measured in radians. Okay, if you take radius of 5 and then you multiply it by 60 degrees and get 300, okay, that's not going to work. Okay, it needs to be in radians. If that theta is not measured in radians, then we cannot use this formula. So then what would we do then if it was given to us in degrees? Convert it to radians first. If we can convert it to radians, then we can use the formula. Fair enough? Okay, question so far? Alright. And of course, we can write the formula in terms of degrees by using the conversion and putting it right into the formula. So notice that what we did here, instead of S equals R theta, all it is R times theta times pi over 180. Because ultimately, what does that pi over 180 do to the theta? It changes it to radians. Fair enough? So you can actually use this formula if you'd like, or you can just convert it first and then use the previous formula. So we do have two versions of the formula. They're really both the same. One converts to radians, and one is already good to go with radians. Okay. Questions so far? Alright, so let's take a look at this example here. It says find the perimeter of a 30-inch slice of pizza of a large 8-inch radius pizza. Okay. So keep in mind that this circle was my pizza, and I have a central angle of 30, and the radius of this thing is 8. Keeping in mind we want to know the perimeter of the piece of pizza, okay, the distance around it, if you will. Well, it would be 8 plus, we call that S because that's the arc length. Fair enough? And so from that, we could say that the arc length equals R times theta. However, the measure of the angle is in degrees, so we'd want to change that first or use the other formula. Doesn't really matter which one we do, we can choose. Okay, but if I go 30 degrees times 180 degrees and pi on top, and then we reduce that, it turns out to be pi over 6. And so with that side, we can say 8 times pi over 6, and we could get 4/3 pi as the arc length. So radius times central angle measured in radians. And so with that said, then our perimeter then is going to be 16 plus 4 pi over 3. Now, if they wanted that in decimal form of some sort, of course, we could just put that in the calculator and get a decimal for that. Okay, but depending on how they ask it, okay, we might give an answer that's in terms of pi. Okay, in the case of an actual perimeter of the piece of pizza measured in inches, it would probably make the most sense to multiply that out and get an actual answer in inches. That would mean something to most people. Okay, so we can go ahead and do that as well. But key issue is making sure that we can find that arc length, which is the ultimately the crust part of that pizza, if you will. Okay. All right. Okay, I want to look at a couple things to finish up here. The next part is what we call angular or linear motion. Okay, when we talk about an angular speed, okay, we're using units like revolutions per minute. And when we talk like a linear speed, we use like miles per hour. Okay, if we're driving down the highway, we're going in a linear manner. Okay, but if you think about your wheels on your tire, what are they doing? They're going around in a what? Going around in a circle. So your tires are going to have some kind of angular speed, okay, some kind of revolutions per minute. In fact, if you look at your car, you'll notice that there's a device that tells you how many revolutions per minute your engine is working at, okay, because your engine's turning around in circles. Okay, not the engine itself, but the parts in there. But ultimately, that's in revolutions per minute. You might know what that device is called in your car. The thing that measures the RPMs. It's the tachometer. It's another good thing you can tell your friends at lunch. Okay. All right. And I want to look at on page 354. There's an example I want to look at here. It says that Albert Juarez's truck has wheels that are 36 inches in diameter, and it says if the wheels are rotating at 630 revolutions per minute, we want to find the truck's speed in miles per hour. So keep in mind we're looking at changing this time from an angular speed to a linear speed. So we know that there's 630 revolutions per 1 minute, it says. So we're given a rate, an angular rate. All right, and keep in mind we want to go to miles per hour. So the first thing that we're going to do here is we're going to get the minutes out of there and bring in hours. So I'm going to put in minutes up top, bring hours down to the bottom. That gets rid of my minutes. Okay, and now I have revolutions per hour. Okay, but I don't want revolutions. I want to somehow change revolutions to this linear unit of miles. Okay, so I want to get rid of revolutions, so that's got to go down to the bottom. Okay, and what I can do is I can bring in radians, because radians and revolutions are related to each other. Okay, so think about that. If I have a 1 revolution of a circle, okay, that's going to basically go for a distance of 2 pi. Okay. All right, so we're going to go 2 pi radians for 1 revolution. Okay, and then here's where we bring in the actual part about the actual size of the tire. Okay, because this ultimately is true for a circle of radius 1. 1 revolution is going to be 2 pi radians. Okay, and if it's a bigger circle, we don't want radians either way, so we're going to get rid of radians. Okay, and we're going to bring in the linear unit of inches. Okay, and in our case, 1 radian is going to be equal to the 18 inches. That is the radius of the tire. Okay, all right. Still not done yet. We do have revolutions out. We do have radians out, but at this point, our answer is in inches per hour. So once we take care of the converting to linear by doing those two, then we can get rid of our inches by bringing in feet, and then we can get our feet out of there and bring in miles. I'm running out of space here, but ultimately 1 foot 12 inches, 1 mile 5,280 feet. And then from there, the other conversion we know we have here is 60 minutes and 1 hour. And once we have all that added in there, we can multiply the whole top and get an answer. We can multiply the whole bottom and get an answer. And then last, we can divide those two. And that'll give us our miles per hour. Turns out, if you do all that math, turns out to be 67.47 miles per hour. Okay. All right, so if we're going to change from an angular speed, a couple of key components again. If you want to get rid of revolutions here, you're going to want to relate it to radians. Okay, 1 revolution is always going to be 2 pi radians. But then you can get rid of radians by relating the radians to the radius. Okay, so whatever the radius is, had the radius been in feet, then we would have had 1 less conversion factor over here, wouldn't we? Okay, so the radian measure, okay, and the number of inches or whatever for the radius, okay, those are going to be that second relationship, and this is probably the key relationship right there that brings in the actual size of the tire. Because if we had bigger tires, okay, 1 revolution would make it go further. All right, there's one last point that I want to discuss real quick, and then we're finished with our notes here. There's one other type of distance that we call a nautical mile. Okay. All right, and a nautical mile obviously is going to be used at sea. Okay. Nautical means water. And so this nautical mile, we also call it a knot. So if you're watching a show where they're in a boat, sometimes they're talking about their speed is 35 knots. Okay, and that ultimately means nautical miles per hour. Okay, all right. So what it boils down to is this nautical mile is measured as the length of 1 minute of arc length along the Earth's equator. Okay, you do not have to memorize that fact. Okay, but what we're going to look at then with that information is there are a couple of conversions. Okay. So if you look at the first conversion, a statute mile, that's like our normal mile, okay, is going to be equivalent to 0.87 nautical miles. And then going back the other way, 1 nautical mile is going to be 1.15 statute miles. Okay, so notice that they're close to each other in terms of being almost the same. But if we go a whole nautical mile, then we actually went more than our normal mile, didn't we? Okay. And so how might we convert something like that? Well, looking at, say, number 50 on page 358, they give us 257 nautical miles. Okay. And so just like any other conversion, we're going to put nautical miles on the bottom and bring in miles on the top. And we know that 1 nautical mile is 1.15 statute miles. Okay. And then from there we could do the math by multiplying and get our final answer. Keep in mind that you could use either one of these conversions that you chose. You could have put 1 mile here and then 0.87 down here and gotten the same result. So instead of multiplying by 1.15, we could have divided by 0.87. And it doesn't really matter which of the two conversions you use. Okay, as long as you get the units in the right places, that's the key element. Making sure that you put the units on bottom if you're trying to get rid of them in this case. Bring in the units on top that you want. Okay. Questions?